Uh, all right. So welcome to the second session of the live problem solving schedules that we are having every Tuesday, 6 p.m. to 8 p.m. Under the course CH20, that is Mass, Momentum, and Energy Balances in Engineering Analysis. So this was the previous stuff that we did earlier. And today we'll be doing, just give me a moment, please. 1 and 2 and 3, okay? Yeah, so basically, this is February 14th, 2023. And I'm not sure, we've got a weird guest here who does not respond. Can you hear me, please? Hello? Good evening. So anyway, let's not care about them. So, if you might have looked at the week 3 content, so the last two lectures are based on numerical methods for solving nonlinear algebraic equations. So today, we'll be discussing some problems on nonlinear algebraic equations, and we'll be solving them starting from scratch. And I'd also like to give you some flavor of how actual physical world problems are being formulated. So I hope you look forward to it anyway. So the first problem of the day that we will be starting is all right. So in this case, let me pick up one problem. Well, you might have heard about flows through a frictionless pipe, right? You usually use the partially flow equation to model flow inside the pipe, and it gives you something like a velocity profile where you are assuming this to be the pipe. That gives you something in the terms of f of r squared, a function of r squared. That is, and r is the distance from the center right here. So the key point here is that the flow is considered laminar. And laminar flow, of course, I won't be repeating all the theory behind this, but the Reynolds number is typically less than 2300. That is a general benchmark. It could be more or slightly less, but this is considered as a general benchmark right here. So consider a flow with a Reynolds number of approximately 1e5. And this is basically the computational notation for 10 to the power 5. And having a 10 to the power 5 Reynolds number flow implies that you are completely in the turbulent regime, especially when you are talking about closed channel flows. Now, there is something called a friction factor. You might have heard about it in your basic fluid mechanics course. Something like the friction factor F. This is also sometimes known as the Darcy's friction factor. Now, there are several equations to represent this for turbulent flows. And one of them looks something like this. You might have heard it about a lot about it in the Moody's chart that is made something. You see, you mark out graphs and then check out something like checking out the uh, maybe epsilon by d ratio, roughness by diameter, and then you check out the f value right here. So that's the Moody's chart. So I won't be going, of course, not be covering the details for the same, but you could get a slight idea. So this is log 10, and this is RE times root f. Now, since the numerical methods actually are slightly problematic when you consider that f is the form of the total equation, and that is equalized to 0, so we will be replacing f with z for no chances of confusion between f and z, of course. So let us assume that z is the new representation for the friction factor. And now the new equation becomes 1 over root z equals to minus 0.4 plus 4 times log 10 Reynolds number, that is 10 to the power 5 root z. So this is a basic form of the equation that we've got here. And we need to solve for z. Now there are, as discussed in the lecture parts, there are several methods to solve for z. One of them is the successive substitution method. Now, what you do in the successive substitution method, let's call this the SSM. So what you do in the SSM is to assume a starting value of z, let's say z naught. And then you solve this, you put this z naught value in one of the expressions, and then obtain the z1 value from a particular expression for z. Using that z1 value, you put it in the bigger expression on the right-hand side and obtain the z2 value, and so on, until the zn minus 1 and zn, the values that you are calculating at maybe the nth step and the n minus 1th step, are arbitrarily close. So these are basically the convergence criteria you've got. So it could be zn minus zn minus 1 modulus of less than something like some tolerance, some given finite tolerance. Let's say sometimes it is 1e minus 5, sometimes it is 1e minus 4, sometimes it is 1e minus 8, but it could be anything. And another possibility is that, so this, since we're calculating the roots, the functional possibility does not arise at the moment. All right, so anyway, so here we are calculating the differences. This is one of the convergence criterion. There are several others in the case when you are representing the equation via functions. So what you do is that you could have something like the value of the function at the nth step minus the value of the function at the n minus 1th step could be less than some certain tolerance, or you could have like maybe the value of n at nth step minus the n minus 1th step divided by zn minus 1. This could be something less than tolerance, or you could also have a relative error concept, that is zn minus 1 divided by zn minus 1. Modulus of entire thing could be less than a certain tolerance. So here are the different approaches for. These are all your stopping criteria. You know, once you start an iterative procedure, you need to stop at a certain point. So the stopping criterion is defined by this formula, and this is reasonable, right? As soon as the root values at different steps start to converge. That is what you mean by convergence, right? Suppose Zn minus 1 is here, suppose Zn minus k is here, Zn minus 2 is something here, Zn minus 1 is here, Zn is here. So you're gradually converging to a solution. That is what convergence is all about. So this is your stopping criterion. Okay, coming back to our problem. So there are two, typically you see, there are two instances of Z in this particular equation. One instance, let me change the colors right here. One instance is here. You have one Z here and another Z you've got here. All right. So if you want to successively substitute for different values of Z, you could have the entire equation approach it from the left-hand side, that is calculate Z from here, or you could have another form for Z that could be calculating Z from here. That is, you just manipulate this equation, bring the 0.4 to the left-hand side, divided the entire thing by 4, take the 10 base 10 exponent and divide by 10, divide by 10 to the power 5, and then square it. Of course, you get Z. So as far as I am aware, the tutorial provided to you in the week 3 lectures, or it might be just week 4. Yeah. Anyway, I think it's the last lecture of the week 3. So in that case, you are being provided a value of Z from the left-hand side. So it is being written like this. Can you hear me, please? Hello? Excuse me. Oh, hello, hello. Can you hear me? Well, you are intruding every now and then, and you are not speaking anything. So how do I assume that you are not here to create trouble? Can you speak something? Are you a human or a robot or a bot or something? If you are a human, then just do something, raise your hand or speak out something, do something. But I cannot hear you. Would you like to rejoin? I think you can hear me, right? If you can hear me, could you write something in the chat box? Because I cannot hear you. Maybe try joining through your cell phone. or something else? Or maybe try using some earphones or headphones if your microphone is not working, or change them. Okay, so we'll probably have to wait for this person now. Maybe raise your hands, or maybe raise your hands, but I cannot hear you. Human, pure, are you a robot or a human? There might be some connection problems in that, guys. Um, Joining link. So anyway, so what the what the lectures have done is express this part as 10 power 5 root of z, and you are just squaring the entire thing. That gives you one value of z. So of course, since this part is already covered, what we'll be doing is we'll take the other approach. So I think that will show the difference clearly. And we'll be taking the other approach as, let us consider this part as 1 by root z over, take the 0.4 right there, divided by 4 both sides, and this gives you
Hello, sir.
oh, good evening.
Good evening, sir. Sorry for interruption, sir.
No, that's fine. So, would you like to, are you comfortable with me continuing in English, or would you like to mix some languages like Hindi or something?
Sir, I can speak in Telugu, sir, actually.
So that's perfect, I guess. So we don't need to switch to Hindi probably.
Oh, yes, sir.
All right. So I think I introduced myself in the last session, and you were trying to probably join in the last session as well. But unfortunately, it was don't think you were able to join last time, right?
Yes, actually, I tried, sir. Same problem. I think in the laptop, same problem. Like today, it happens, sir.
Oh, no,
I
no,
tried.
no problem, no problem. I was
Today,
worried that you were some kind of robot. You know, these days there is a trend of AIs and
no,
chatbots.
no, sir. Right now, I'm using phones. Before I tried in laptops, sir, but it is
Okay,
not.
okay. There's no problem, no problem. So, since now I have a human attending my live session, so I would like to ask you if you want to, uh, means have me repeat something, or well, because are you getting an idea of what we are doing today?
I think about the nonlinear algebraic equation solution, uh,
Yeah, exactly, right.
matrix solutions.
Yes, right.
Sir,
So,
sir, can you explain the successive substitution, sir?
right. So, should I go into the theory part a bit? Uh, before solving this entirely, or should I just continue with the problem right here? So
Okay,
what
sir.
would you suggest? What would you suggest? This is your choice.
Actually, actually I didn't hear before class, so that's why I don't know what I'm saying.
Okay. So I'll go into the theory part a bit, and then we'll start with the problem. Okay.
Okay, sorry, sir. I really sorry, sir.
No, that's fine. I was just worried that you were that it was some kind of problematic element in the chat that's
Yes, sir.
interrupting continuously.
Yes,
That's
sir.
perfect. No problem. No problem. No problem.
I can
I
hear
have.
your voice, sir, but my voice are not hearable to you, sir, in that time.
Yeah. So no problem. I appreciate that you attend, or you are at least attending the live session, because last time as well did not have anyone, so it was just me hearing myself.
Sorry,
So
sir.
anyway, that's perfect. So what I would like to say here is that now we'll go into some details. Assume that you have a curve, okay? Let's say
Okay.
it looks something like this. Let's say this is f of x, and this you have x. And you need to solve for f of x equals 0, okay?
Okay, sir.
Now this f of x could be a polynomial, let's say polynomial, that could be of the form maybe x to the power 4 plus, let's say ax to the power 4 plus bx to the power 3 plus cx to the power 2 plus dx plus e equals to 0. Or it could be of some transcendental form that could be something like, e to the power x plus a to the power x plus b e to the power minus 2x plus c equals 0. Or it could be something else. Just the key concern is that the function that is f of x is a function in a single variable that is x. And this x could be anything, y, z, w, anything. So this is just
Yes.
a form of the representation, the symbolism. And another part could be something like a trigonometric function. You might be well aware of what trigonometric functions are.
Yes.
So I don't think I need to mention that here. So now if we want to consider, now sometimes, if you have a simple equation, for example, you've got x squared minus 5x plus 6 equals 0. So
Yes.
it is probably easy to solve this, right? You can just write x minus 2x minus 3, and this becomes 0, right?
Yes, sir. Yes, sir.
And this gives you like x equals 2, x equals 3. Now you have two roots right here because the degree of this polynomial equation is 2.
2.
So this becomes, and just quickly plotting the graph, put x equals 0 here, and you'll be getting f of 0 is equal to 6. So
Yes.
at 0, the value of the graph is 6 right here. And here you've got 2, here you've got 3. So the graph will look something like this.
Yes, sir.
I'm sorry for the poor design, but this is really smooth right here. Okay.
Okay.
Now, but what if you have a really weird equation? For example, like x power 5 minus 5 minus 3x4 plus maybe 4x cubed plus 2x squared minus 19x plus 1. I presume that you understand that it is almost impossible to solve it using factorization, right?
Yes, sir. Yes.
Yeah. So to solve these types of equations, we would like to use some other techniques that do not require so much of an effort from our sides. Now, what is the key point here in chemical engineering or in any type of engineering,
Yes.
we do not need exact solutions. There are two types of solutions, For example, there is a certain value right here. We are getting x equals 2 and x equals 3. And these two solutions are exactly satisfying this particular equation, right?
Yes, sir.
But what if I say that I give you an answer that it is 2.00001 and it is something like 2.9998.
Yes.
So this should be probably acceptable to you because we are talking about engineering, not mathematics, right?
Yes, sir.
So this is the reason we are not looking for exact solutions, but we are looking for practical solutions.
Okay, sir.
The solutions that will actually work for our problems and require the least amount of effort to calculate. Okay. So here you might be thinking that it is really easy to factorize, but here it is almost impossible to factorize, right?
Yes, sir.
Okay. So to solve such problems using numerical techniques, we have a bunch of, different types of algorithms, different types of approaches, and a lot of them have been discussed if you check out the week 3 content, week 3 videos,
Yes.
the last 2 videos.
Numerical methods.
Yeah, so it's called something like macroscopic balances and all solving systems for those. So they have discussed a lot of approaches, and we today we are taking up those approaches themselves. So one of the first, so what we'll be doing, we'll be maybe I'll tell you all those approaches one by one, and then we'll just apply it to this problem.
Okay, sir.
Or maybe we could pick up a simpler problem at the moment. Okay,
Yes.
so
Yes.
let's say the first thing is successive substitution. This would probably be the easiest approach that you could ever have, but
Yes.
it requires a separable separable x, you could say, maybe. Okay,
Okay.
for example, you've got something like x to the power, let's say, let's take a cubic equation, okay? X power 3 minus x squared plus x minus 1
Yes, sir.
equals to 0, okay?
Okay.
So if you just so why are we taking this type of equation? You can actually factorize it as like this, right? X minus 1 equals to 0. And this becomes
Yes.
x minus 1, x squared plus 1 equals 0.
Yes.
So one of the roots of this equation is x equals 1. And the other root of this equation is x equals 2. Plus minus iota, right?
Yes.
Do you understand iota and imaginary numbers?
Yes, sir. Yes, sir.
Okay, that's perfect. Okay. So this is not practical, we are not concerned with this root in engineering applications, at least for now, because in chemical engineering you've all got practical applications. So and in electrical or signal processing types of applications, you might be actually required to have this, to have your phase differences and to
Yes.
have some signal modular frequencies or something. So for them, it is relevant. For us, it is not at the moment relevant. Now, we will be starting the successive substitution method right here, okay? So I would appreciate it if you could pick up your calculator and start working out right with me. So that would be really, really meaningful, okay?
Okay, sir.
So are you ready?
So wait 1 minute, sir. I will take
Sure,
it.
sure. No problem, no problem.
Yes, sir. I'm ready with the calculator.
Okay. All right, so that's great. So in the case of actually, simpler problems like these, you need to have something called an initial guess, okay? Let's say at t equals 0, at time equals 0, you've got an initial guess that you supply for this problem. Now, the question is how to choose this initial guess. So somebody, could guess x naught as 0, This is just a guess. It could vary from person to person, right? Or
Yes.
someone could choose it as maybe 10,000. Someone could choose it as 0.099.
Yes.
There could be a bunch of options, right? So
Yes.
we need to have a concrete protocol
Okay.
for a good guess. A good guess will always lead to good solutions.
Yes.
So for a good guess, this particular protocol, usually they do not tell you how to do that, but through experience, I feel that this method is good, at least for the simpler parts that are encountered in usual engineering applications. What you could do is just understand where the function changes its signs. Okay, sign means
Yeah.
positive, negative. For
Okay.
example, the simplest value that people can think of is 0, x equals 0, because at x equals 0, many of x terms become 0. So it is easier to calculate, right?
Yes, sir.
Now, consider this part, okay? Let's say this one, this original equation. So we've got fx equal to, or whatever you have right there.
Yes.
Wait, let me just pull it up. This one, okay?
Yes, sir.
Now, put x equals 0 right here, and you'll be getting -1, right?
Yes, sir.
So we know now that the curve passes from this point, that is 0, -1. Now, you could also put, simple values like, let's say x equals 1, put it here. And surprisingly, you are getting that x equals 1 leads the entire thing to 0.
Yes, sir.
That is just a coincidence, if it might be 2, then you will not be getting 0, okay?
Yes, yes.
So this is just for our verification part. So we know that now let's say that you are putting something like x equals 2. This is also simple value. So for x equals to 2, this entire thing becomes positive, This is 8 minus 4 plus 2 minus 1. This becomes greater than 0.
Yes, sir.
So x equals to 2. You know that you don't care about the value, okay? You just know that the function is somewhere above the x-axis.
Yes, sir.
And at 0, it is below the x-axis, right?
Yes,
So
sir.
that means that it is going something like this. We don't care about what is happening here. It might be like this or whatever.
Okay, sir.
We just know that at x equals 0, the function is below the x-axis, and at x equals to 2, it rises above the x-axis. So the root of the problem, at least one root, there might be hundreds of roots, but we don't care about them. We just talk about a single root. At least one root will lie between 0 to 2. And you could
Yes.
just open this interval, because you know that 0 and 2 are not the roots of the function.
Yes, sir.
Okay?
Yes, sir.
So once you have this, you can just, let's say we take a guess value of 0.5, okay? We assume that the root of the equation is 0.5. You
Okay.
could further, refine your guess by putting the value 1, but since it goes to 0, coincidentally, right here, we won't be taking that value. Now, let's go to this part. This entire equation can be written like this.
Okay.
Do you agree? Do you agree?
Yes, I agree, sir.
Okay, so this is x naught equals to 0.5. That is our first guess. And what you do now, that to calculate x1, see, the successive substitution method has 3 parts. One is successive, one is substitution, and one is method. So the successive part
Okay.
means that you are doing things step by step, one by one. You do one thing, then you continue with the other, and then you continue with the other after you complete the second thing. And substitution means that you are substituting some value into some function, okay? For example, you're fitting x value into f of x, right?
Yes.
So if you have x naught equals to 0.5, then for calculating the next successive value of x1, this x naught must be substituted somewhere, right?
Yes, sir.
And for that purpose, we have this thing, the entire right-hand side,
Okay, sir.
x naught squared minus x naught plus 1, okay?
Okay, sir.
Now this x1 cube would be 0.5 squared minus 0.5 plus 1. This would be 0.75. Am I correct? Yes, I think I'm correct, right?
Yes, sir. Yes, sir.
Okay. So then x1 would become, if we take the just the real part of the real value of this, then x1 would become something like 0.9086, right? You can check it with your calculator if you have one.
Yes, I am trying. Yes, sir. 0.9086. Yes, sir.
Okay. Okay. Great. So
Doing it,
yes.
sir.
So now what you'll be doing is that
It is
you check. Sorry.
yes, sir. It is new rule. I think we have to substitute in the function f of x equal to x cube minus x square plus x minus 1.
Yeah, right, exactly. So now what you'll be doing to check if this is actually a root of the original equation, you just substitute this as in x1.
Yes, sir.
But in this case, substituting 0.9086 will not give you 0.
Yes, sir.
And that means you need to go further. Okay.
Yes, sir. Yes.
Then comes the step 2, and the substitution equation is actually this one. So what you do now, in the step 2, you get x2 cubed equals x1 squared minus x1 plus 1 equals to let's say this 0.9086 squared minus 0.9086 plus 1. This becomes something like 0.9169.
Yes.
Okay.
Yes.
And then x2 becomes 3. This becomes 0.9715. Okay.
Okay, sir.
Now again, you'll be substituting this value in f of x, and then you'll find it again that this is not equal to 0. So we are still away from the root. So we need an additional step right here. We write the same thing. This is x2 squared minus x2 plus 1. And this is something maybe x3 equals to, can you tell me what the value is right here?
I will solve.
Sure. Take your time. No problem.
Minus 1.0. Oh, sir, can you hear me, sir?
I can hear you right.
Yes, sir. I will done this. 0.9723, sir.
0.9723. Okay. Again, so I mean, f of x3 is also not equal to 0, right?
Yes, sir. Yes.
So we actually notice that although we are getting closer and closer to x equals to 1, we
Sorry,
are
sir. Actually, I said it is a x cube value, sir.
Okay.
Actually, is 0.99068, sir.
Okay. 0.99068. So that becomes 0.7 approximately, right?
Yes, sir.
Now, there is one thing in engineering problems that you really need to be consistent at, the number of significant figures that you are keeping in your solutions. So if you're keeping around 5 decimal places, because this actually is a lot important to consider, because, there are some equipments that give you 5-place precision, and
Yes,
there are some equipments that give you 4-place precision. So if you are reporting your values in 4 decimal precision, then you must keep that in mind. Okay. So even if you are getting a value 0. Let's say 0.991, then you have to report it like this.
yes,
Add an extra 0 so that it is clear that you are working with a 4 decimal precision point.
yes, sir.
Okay, so just a quick tip right here. Anyway, so we know that we are getting closer to x equals to 1, but we are not actually getting x equals to 1. So maybe in a few more steps, you might be having, let's say, xk equals 0.99998 something. So this
Yes,
is really, yes, so this is really, really close to 1, but it is not 1. But it is sufficiently accurate for our practical applications, right?
yes, sir.
So that is the key point. So now this is all about the successive substitution method. So did you get a hold of it? For example, if you have some other problems, would you be able to apply it?
Yes, sir. I understand.
Okay. Now, a natural question from this type of problem arises that, well, you've got this type of function, it is x cubed, it is x squared, it is x, and it is 1, okay? So
Yes,
you only took x cubed equals x squared minus x plus 1, but what about the other possible combinations? For example, you could just take maybe this one, x equals, x squared minus x cubed plus 1, or let me just write it well, minus x cubed plus x squared plus or minus?
oh,
Minus 1, yes. No, plus 1.
okay.
Yeah, it's plus 1. So you can also write it like this. There is no problem right here. But then again, you'll have to do the same thing. For example, if you take a guess, let's say x equals to 0.5, x not equals to 0.5, then you'll have x1 will be equal to 0.5 cubed. That will give you minus 0.125. Just correct me if I'm wrong, and then 0.25 plus 1, this is 1.25 minus 0.125, that becomes probably 1.125, right?
Yes, sir.
So then go to the step 2. Just wait, I'll set up a function right here. Alpha. X squared plus 1. Yeah, for 1.125.
Yes,
So if you do this now, x2 equals to, minus x1 cubed plus x1 squared plus 1 equal to something like 0.8418, right? Yeah.
yes,
And again, calculated for 0.8418. This becomes x3, step 3. X3 becomes 1.121. 1.1121, right? And this keeps going on until you are getting something, that's what I described earlier. You need to have some stopping criterion.
Yes, sir. Yes.
So you can, go as much as you want, but there will be a certain stage when you're getting really close to 1. So, but this time we know that the solution is 1. But what about the other times when we do not know what the solution is? So
Yes.
we need to have some mathematical and rigorous stopping criterion for stopping our iterations. Okay, so for doing that, what we usually take up is xn minus 1 modulus would be less than a certain tolerance criterion that is described by the user.
Yes.
By the user, or maybe the user really requires a really accurate solution, so they'll be suggesting a 1a minus 8 times type of tolerance. This means that when the difference between two successive steps, the roots of the steps that are being given using this particular SSM method, the difference between them could be up to the 8th decimal place, this type of thing.
Yes.
8 decimal places. Then you are actually stopping the solution. Typically, in most practical applications, we are usually keeping a 1e minus 6 or 1e minus 5 tolerance. So this e is basically a computational notation. It is just equivalent to 10 to the power minus 8.
Yes.
Okay, so in this case, you can specify a certain tolerance, and you could just, stop when you reach satisfy that particular criterion that you set up. So this is all. Yes, so this is all about the successive substitution method. Now, would you like to apply it to this one?
Yes, sir. We will do so. Yes, sir.
Okay, so let's rewrite this equation for a moment.
Sir, if we have two equations, then how can we assume the function, sir? In the video, there is two equations, sir. Hello, sir. Can you hear me,
Okay,
sir?
yes, I can hear you, but what you are talking about is a system
Yes.
of
Yes.
nonlinear equations. As I said, at the moment, the type of equations that we are discussing, you got to have a single variable x.
Okay, sir. Okay, sir. Okay.
Yes, so there might be its name might be different, but it will be a nonlinear equation, a single equation. If you have two
Yeah.
or more, yes. So if you have two or more than two equations, then that means you have the same number of variables. For the system to be consistent, the number of equations will be equal to the number of variables.
Yes, sir.
So those are those types of problems. Yes, you can solve using the successive substitution. It is a form of a Gauss-Seidel method.
Okay, sir.
But that we are not going to cover today, of course. And
Okay.
these methods are usually really computationally expensive. So you typically are using mostly LU decomposition, or
Yes.
you are using the Newton-Raphson method, or you are using the QR decomposition. You go into those matrices and Jacobian parts. So
Yes.
these methods are not preferred. These are a waste of time.
Yes. Okay, sir.
So anyway, so the next time, if you actually want to join next Tuesday, then if you want, I can show you some programs, like some codes. Do you know how to write codes in MATLAB?
Actually, in this session, I'm learning, sir. I took that subject too, sir.
Okay. So if you want, we can pick up some codes for these types of methods where they're using loops and conditions for tolerance. So that depends on you. If you want to, just let me know.
Okay, sir.
Yes, so okay, so let's switch to the next method. Okay,
Okay.
now we'll do the bisection method. So as usual, I'll be giving you a really quick overview of what's happening in the bisection method.
Okay, sir. Actually, I learned those and as for a single equation, I can do myself, sir.
Okay.
Bisect,
So
node adaptation method, succession, secant method. I can do in myself, sir.
okay, so so we'll just start. We'll directly jump into the problem. Okay,
Yeah, okay, sir. Okay, sir.
because this session is actually organized for problems. So
Yes,
we are expected to solve some good problems over here. So we'll do that. Okay.
yes, sir.
So in the video, you might have noticed that they have used this form. Okay, so let me explain the problem again. Okay.
Okay, sir.
So there is a pipe,
Okay, sir.
and there is a certain fluid that is flowing through this one. So usually, if you have low velocities of the fluid, then this regime of flow is called laminar flow. Do you know about? Have you done any course in fluid mechanics or something?
Yes, sir. I am chemical engineering student, sir. I'm right now doing PhD, sir.
Okay, that's great. That's perfect. So, you know about laminar flow, right? So for channel flows, you've got an approximate, a generic. This is a rule of thumb. So it is not exactly accurate, I'd say, but it works in most types of applications. So if your Reynolds number is less than 2300, then you can call it a laminar flow for channel flows. So what we are assuming that we want to calculate the friction factor. This is the Darcy friction factor that is given by this equation for turbulent flows, not laminar flows. Okay,
Yes, sir. Yes.
for laminar flows you can just I think you might be remembering this type of equation that you get.
Yes,
Yeah,
sir.
so something like this. Maybe I'm wrong, but this looks like something like this. Okay,
Sir. That's
so sorry.
yes, sir. It is that's fraction vector, sir.
Right, exactly. So, so for turbulent flows, you might have heard about Moody's charts where they correlate the relative roughness with the friction factor, and then you match the graphs and all those things. So that is one part. Now, we have at this point of time, we do not need to go to the graphing parts, but we have a simple equation that is given here, this one, and we'll be using this equation to calculate f. So I'm not calling it f right now because we are always using f of x as a
Yes,
form
yes,
of a function. So if we keep using this, then it might just confuse you further when you're looking at the notes or something. So we will just replace f by z or z,
yes.
as you call it. Okay, so for the ease of our understanding at the moment. So again, you have this equation right here, 1 over root z equal to minus 0.4 plus 4 log base 10, or Reynolds number root of z. Now, what you'd be doing is, in the video, they have used this type of form. This is minus 2. So z equals minus 0.4 plus 4 log 10. But you can calculate this, right? Because assuming that this is never 0, you can just take a reciprocal right here and then square both sides to get this. This should be easy, right?
Okay, sir.
Can you see this from here, right here?
Yes, sir. I can see, sir.
Yes. Okay, great. So, but let us, twist the problem a bit and approach this problem from the right side. I already told you that there are multiple approaches to the same problem in the case of successive substitution. For example, you're talking about x cubed, and you can approach it from x, you can approach it from x squared, or you can approach it from x cubed. So it's all up to you. So let's do things slightly differently. So we are using this form of the equation, this one. Okay.
Okay, sir.
So this would give, root of z equal to 1 over 10 power 5. And you can write it as 10 to the power 1 over root 4, 1 by root z plus 0.4. All right.
Yes, sir.
And if you notice really carefully, you can just write it, you can just simplify it more as this entire thing might just be written as, I just noticed it could be written like this, root z plus 0.4 minus 5. Right?
Yes, sir. Yes.
And this can maybe further be simplified, like for root z minus 4.9. This is perfect, right?
Yes.
And if you directly want your solution without the need to square, to just square both sides. And then this entire thing becomes 1 over 2 root z minus 9.8. Do you follow?
Yes, sir, I'm following.
Okay, great. So here we go. So we've got this equation where it is looks something like this: 2 root z minus 9.8. So let's start with multiple methods right here. So first is the successive substitution method. So what do you want the initial guess to be? I mean, do you want to suggest some value for z naught? Maybe. Look, we cannot try 0 here because this part will become undefined.
Yes, sir. That's why I said 4, sir. Like easy to calculate next one.
Sorry, I didn't get you. What?
Yes, sir. That's why I didn't say the 0, sir. I said 4, sir.
4. Okay, so you want 4. Let's say that you're talking about 4. Okay. So let's start with 4. No problem. So the further you are from the root, of the problem. Let's say you're starting from here. Let's say this is z naught, and the root is here. This is z star. Let's call that. So the further you are, the longer it will take to converge. That is reasonable, right? So
yeah.
Yes, so at the moment we are of course not worried about this. And if you actually want to understand the problem, right? So maybe get a physical insight on how things are happening inside, then you could just do something like this. So
Yes.
let's say that we want to have a graph for 10 to the power 1 over root z, okay?
Yes.
So this is something like, if you put z equals 1, it will be 10. Z equals to 1 is something like 10 maybe. And if you put z equals to 4, then this becomes less than 10, okay?
Yes, sir.
This is root of 10. That is something maybe 3 point something like this. And this is just a bit of mathematics, if you want to continue the geometric interpretation, then I can continue, else we can just jump into this one. What do you say? Should we try to visualize what's happening here, or we should just start solving the equation?
Start solving the equations.
Okay, that's that's the way to go. Okay. Great. So
okay, so what you can tell, sir. I'm listening, sir.
no, if you're interested only, then it makes any sense, because this is not exactly relevant, but it will give you a physical picture of what's happening inside.
Yes, sir. Yes, sir.
So again, what do you want?
So tell geometry things.
Okay. So Now if you see that something like z equals to 9, this will further reduce this thing, right?
Yes.
And now if you add a 2 here, so let's say that we are talking about z equals to 1, then it will be further compressed to a certain low value right here, let's say here, okay? And this 3 would be further compressed to an even lower value, and this one would be compressed to an even lower value like this, right?
Yes.
And at z equals to 0, this entire thing becomes very, very large. Something like this, asymptotically infinity, okay?
Yes.
So it's, it starts from somewhere here. And now this entire thing is being scaled by something like 10 to the power 10.
Okay.
Because you can just write it minus part as below here, right? 10 power 9.8 here.
Okay, sir.
You get that, right?
Yes, sir.
So anyway. So this entire thing, the magnitude of this entire thing is being reduced by an order of 10 to the power 10. So it goes further down here. So I don't need to represent it further down because we need to have a certain scale right here. So we can assume that the graph is going something like this. And at z tends to infinity, this entire value becomes 10 to the power 0, the limiting value, minus 10 power 9.8. So this becomes really, really close to 0, but not exactly 0.
Yes.
And on the left-hand side, you've got, let's say, y equal to x. So how does that look? That looks something like this. Okay?
Yes, sir.
So both of these curves are intersecting at a certain point, this. And of course, that is lying between z equals to 0 and z equals to 1, right?
Yes.
Now, if you want to have an even better initial guess, suppose we are like really comprehensive scientists and we don't want to have a little bit of error or any wastage or anything, then what you could do is gauge out the relative values of these two graphs, like y equals to x and y equals to this 10 to the power 1 over blah, 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 whatever it is. And do it at 2 points. Let's say z equals to 1 and z equals to 2 right here, let's say. Okay?
Yes.
So at z equals to 1, this value will be 1 because this is simply y equal to x. And let's call this x now, okay? And at x equals to 2, this value will be 2. All right?
Yes, sir.
And at x equals to 1, this entire curve will become 1 over 2 minus 9.8. Can you just quickly calculate this value and let me know? This is actually 10 to the power minus something like maybe 0.5 minus 9.3. And at x and at z equal to 2, this becomes 1 over 2 root 2 minus 9.8. These two values. I need these two values.
First one value is 5.
What is the value?
5.01 into 10 to the power minus 10, sir.
Okay, so it is a really low value, right?
Yes, sir.
Anyway, so since it is a really low value, in both of these instances, the graph should be lying somewhere like this, right? Even lower, because in both of these instances, the graph is lower than this. So this means that our original part is not correct right here. You get it, right?
Yes, sir.
So this shifts our initial guess even further towards the origin. Did you get this point?
Yes, sir. Yes.
Okay. If you got it, then it's perfect. So, successive substitution, let us assume. So now what you were suggesting was a random guess, okay? That is z equals to 4. Can you hear me, please? Hello?
Yes, sir. I can hear.
Yes, so what you were suggesting is z equals to 4, but just notice how far away that is from the actual value.
Yes, sir.
But now, after a bit of deriving some physical insights from the problem, we are making a more informed guess, that is z equals to 0, 1. So that is the, the benefit of analyzing problem physically before you actually start solving it. You are actually saving a lot of steps. Now imagine this to be a part of your PhD thesis. For example, if you're solving some problem and you are creating a fine mesh grid, something like this, and you supply an initial guess of 4.
Yes.
This is just a representative example. Then your simulation time, the computation time would be something maybe, let's say 2 days. But
Yes.
if you analyze a problem physically and you derive some insights about the relative magnitudes of the curves that you plan to solve, then it might just be reduced to 1 hour.
Yes.
Based on the initial guess. That is why initial guesses are really important, and we should not neglect this step in general, unless you've got a lot of computational power and you don't care about the time that is being spent on solving the equation. Okay, so let's start with z not equal to 1. Agree? Do you agree?
Yes, sir.
Okay, so then let's start. 1 over 2 minus 9.8. This is 10 power minus 9.3. And as you told something, what was the value? Something like 5.xyz, xyw, let's say, not z, into 10 power minus 10.
Yes.
This was the value, right?
Yes.
And the next time you write z2 equals to 10 power 1 over 2 by root times of 5.xyz w, not z again. We're habituated to z.
Yes, sir.
Minus 9.8. Okay. So this gives you some other value. Let's say, do you want to calculate? I don't think actually this is needed. So this is just a process. You already know the process, right?
Yes, sir. Yes, sir.
Yes, so I don't think there's a need to calculate this any further. So you just know that the value that you are going to get is really, really small. So that is the key point that you need to notice from here. So then just go on successively, and as soon as z minus 1 is less than your tolerance limit, you'll get your answer. The next part would be solving the same problem using the bisection method.
Okay.
So you already know how to, what is the theory behind the bisection method, right? Yes?
Yes, sir. Yes.
Okay. So we will just start with this. We just write it 10 power 1 over 2 roots z minus 9.8. So actually, in the present case, you'll have to do some manipulation. In bisection methods, we are not using successive substitution. So you need to have an equation of the form fz equals to 0, right?
Yeah.
So to convert this part into this form, you need to write it as 1 over 2 roots z minus 9.8 minus z equals to 0.
Yes, sir.
Okay?
Yes, sir.
Now again, you are supplying some, let's say, z equals to 1.
Okay.
Z not equals to 1 again. And what you do, let's call this f of z, okay?
Yes.
So you first calculate f of z naught. And you need to have 2, I guess, right?
Yes, sir.
you need to have two initial guesses, well, let me just go through it quickly. If you take Z0 and Z1 right here.
Yes.
Okay. Then the next, yes, so then the next step would be that you take Z0 plus Z1 minus Z1 divided by 2, given that f of Z0 out of f of Z1 is less than 0.
Yes.
Okay, so what we are targeting is that we want to bracket our root, that is this one, let's say Z star, between two values at every iteration, okay?
Yes.
So we need to bracket it within certain the two values at the moment after every iteration. So that is why we need to check if the function actually lies above the x-axis or below the x-axis. So that you could assume that, whenever a function changes nature, for example, it goes from negative to positive, that means there exists a root because it has to intersect the x-axis, right?
Yes.
So the right side of this, if it's an increasing function, then the right side of this would be yielding a positive function value, and the left side would be yielding a negative function value.
Yes.
And so how to know if we are actually bracketing our root is that you multiply both of them. This is just like, plus into minus is always minus.
Yes.
So we are using this technique here to ensure that our root is being bracketed right here. So what you do is you first calculate f0, that is less than 0. And you calculate fz1, which is, let's calculate it together, okay? Standard 0.5 divided by 8. Are you calculating?
Yes, sir, I'm trying.
0.5 minus 9.8.
Minus 0.499.
So this is also less than 0, right?
Yes, sir.
So that implies that we actually cannot use the bisection method right here.
Yes, sir.
So then we need to change the guesses, right? Let's say we are having z equals to 1. And then we have Z1, we replaced it by something like, let's take a low value, okay, 0.0001, let's say maybe. We could try this one. This is effectively 1e minus 5.
Yeah, okay, sir.
Did you get something?
Yes, sir, I'm mathematical error. I think it is a huge number positive, sir. But it is a huge number.
I don't know why the calculator is always showing an error.
Yes, I think it is huge number. I think. Maybe.
All right, so we can just check it, right, by ourselves. How to do that is something like this. Let's say that we are keeping z. Let's say we are further reducing it to this value, so it will be a bit easier to consider the root. Okay, so this becomes something like f of z1 will be equal to 10 to the power 1 over 2, and square root of this 10 to the power minus 6 would be 10 to the power minus 3. And since it is in the denominator, it will just move up here.
Yeah.
So this becomes 1000. And minus 9.8 and minus 10 to the power minus 6. So this is, of course, greater than 0, right?
Yes.
So now we can say that our root is lying between z1. Our root is lying between something like 0.1e minus 6 to 1. Okay?
Yes.
Now, as soon as you get this bracket, the next step would be to calculate z2 as z0 plus z1 over 2.
Yes.
And this will become something like 0.50000005. Okay?
Okay, sir.
Something like this. And then you know, now in the second step, you have two options. So the first would be that between z0 and z1, you have calculated z2, so you've got here, right? Let's say z0, z1, z2. So at z0, you have the value of f is less than 0. At z1, it is greater than 0.
Yes.
Now we need to calculate the value of f at z2. So that would be something, let's say, if it comes out to be greater than 0, which I really think it will be, or it will not be, which I don't think it will be. So it will be probably less than 0 because it is approximately 0.5, you know, and 0.5 is actually what? It is 1 over 2. And if you write 1 over 2 times of root of 1 over 2, this will become 1 over 2 root 2. This becomes 0.7 something, right? 707.
Yes.
And minus 9.8, this gives out a really small value of 10 to the power minus 9.1 something, right?
Yes.
And subtract it from 0. And subtract 0.5 from it, so it will be less than 0. So it's less than 0 right here, and it's less than 0 right here. So what do you think? Do we bracket it within Z0 and Z2, or do we bracket the root within Z2 and Z1?
Z2 and Z1, sir.
Yes, exactly. So here will be our Z3, and then Z3 would be equal to Z1 plus Z2 over 2. Okay?
Okay, sir.
And Z2 is 0.5 or 0.0000 something 5. Sorry, something like that. So Z3 would be something like 0.2500015 times 0.75, something like this. Okay. And now you need to, you know, again, do the same, do a similar exercise. You know that Z3 was an element of Z1 and Z2.
Yes, sir.
So you have the same bisection similarity again, that you've got Z2 here, Z1 here. You know, Z2 is less than Z1, sorry. Is it? Is it? No. Z2 is greater than Z1. So actually, whatever, you know, it is between Z1 and Z2. So Z3 would be something right about here. So you know that f of Z2 is less than 0. F of Z1 is greater than 0. And let's say if you calculate maybe f of Z3, then it will be again less than 0. So again, you'll be taking this interval.
Yes, sir.
So Z4 equals to Z3 plus Z1 over 2. So this is the process
Yes.
that you'll be following in the entirety. And again, you need to specify a certain tolerance. Let's say we specified 1e minus 6. Then you need to ensure that at the nth step, the
Yes.
solution is something less than tolerance. Okay? That is maybe 1e minus 6. So this is all the physical working of these two methods. That's the bisection method. That is the successive substitution method. And another method that you could actually use is the, let's talk about the Newton-Raphson method.
Okay.
So I think you might already be really familiar with the Newton-Raphson method, right? Or should we do a problem? What do you think?
What's that?
Uh, should we do a problem on the Newton-Raphson method, or are you really, experienced with it, so we don't need to cover it? What do you think?
If for single equations, I had experience, sir.
Okay, single equation, you already have experience. So would you
I
like
learned
to?
how to
Yes.
take how to the initial guess.
Hmm.
I learned from this videos. I mean, this session, sir.
Okay.
I
Yes,
never
yes.
think like never think about the geometry or else what the equation is going on. I never think, sir. I just
Okay.
mainly guess something, sir.
Mhm.
Session, sir.
Okay, so that will actually, help you in saving your precious computational resources and time. So
Yes, sir.
as you supply an initial guess that is closer to something that is actually the root of the equation, then it would be really helpful for the solver to really, it will be really rapid solutions. So
Yes, sir.
yes, so the other part would be the secant method. So do you want me to discuss this secant method and the regular falsy if you want? It all depends on you, if had you not been here, then I would have just gone ahead and solved all these problems. But since you are here, so your choices matter to me. So that is why I need to ask you if you want to go into these parts, or we can do something different, probably.
So we can do something different, sir. I mean, these methods I had actually lens for single
Okay.
I did some example in mathematics. I aware of those methods.
Okay, great. So,
Never did
okay.
in chemical science, but I know in mathematical questions.
So can you, like program them into some computer language, maybe? MATLAB or something?
MATLAB is I'm learning some MATLAB.
Okay.
I can understand.
Okay. So should we go into that? But that will actually have a slow, because since I'm not prepared, then writing the code from scratch will take a lot of time. Anyway, so what can we do here is, since you already have learned all these methods, then just maybe wait for 2 minutes, okay?
Okay, sir.
So since you are, already familiar with chemical engineering, so I don't think you actually need to do all those things that were done in the last session, right? That chemical balance and mass balance and all those things. Like they were having some equations like CH4 plus O2 gives something like this, and then you need to calculate the yield of the reaction and the limiting reactant. So all those things are clear to you, right?
Yes, sir, but I'm learning. I'm learning, sir, with careful, sir.
Okay. Okay. Hmm.
In this week, I carefully listen all videos, sir.
Okay, that's good. That's great.
For that, I cannot spend more time, sir. But I learn videos, but somewhere I didn't get, sir. But exactly, I don't know where I am. Sir, element. Um, I want to.
Yes, so it would be really nice if you like want to ask some questions regarding those lectures, maybe. So that is the key point of these doubt solving sessions. So maybe if you want to ask something at the moment, you could do that.
Yes, sir. Limiting extent is there, sir.
Right.
Every time I cannot do in that way, sir. I mean, I am getting something wrong while I'm doing, sir. I may
Uh,
for the
I
limiting.
identifying the limiting reactant, right? That is what you're talking about.
Yes, sir.
Of
Sometimes
course.
I can do easily, sir, but sometimes I didn't get that.
Okay, no problem. So I'll tell you a really simple method to find the limiting reactant. In the videos, as I have seen, they are giving you some big equations, like uh, but keeping some degree of freedom and the number of moles and multiplying everything, taking summation and all. So that entire thing, nothing is required actually. It is limiting reactant, and calculations of excess reactants are really simple. That is, probably the simplest thing that you could ever encounter in chemistry. So
Yes,
it is actually really problematic for a lot of students, but uh, so okay. So what we'll do is that we'll take that classic example that was taken in one of the videos. Think this might just be in one of these parts, right? This one. Yeah, this is right here.
okay.
Okay. So wait a moment, okay? Let me reorganize what I was doing. Let's see what we can do here. Is this a single reaction or is this a double reaction? Wait. Hmm. Let me take maybe a more complicated problem instead of this one.
So without using those formulas, we can do about the limiting reactant and extant reactants, with using only equations. I mean chemical reaction equations.
Yeah, so are you asking a question?
Yes,
Yes, of course. All those equations and formulae are absolutely not required. You just need to look at the reaction and it will tell you itself that what is the limiting reactant and what is not the limiting reactant. So absolutely nothing is required. I was really surprised how people are having such big formulae about the calculations and degree of freedom and all that is stuff is like absolutely irrelevant. Nothing is required. Okay, so let's take this one first because I'm not getting any. I'm getting any questions, but actually, or if you have some question, some problem by yourself, then we can solve that. Or I can tell you my own problem at the moment, and maybe in the next session you could bring your own problems. What do you think?
Question I will ask the ones
Okay,
right now.
so today should we continue maybe?
Okay, sir.
No, I cannot hear you. I think.
Yes, sir. Yes, sir. Yeah. Uh,
No, so should we continue with this problem, or are you bringing your own problem?
that problem, sir.
This one, right?
Yes, sir.
Okay, great. So, what I'll do is just give me a moment, okay? So we will just capture this problem from the original lecture. So that would probably be better because you'll be having the straight away the entire picture in front of you in an instant. Let me do a screen capture right here. Okay. I find this hydrogen sulfide problem. Where is it? Where is it? Oh yes, here we go. Right. Mhm. Okay, so let me start it again.
Okay, sir.
This is actually a fairly good problem according to me. So I hope that this will really help you. Uh, just a moment. Again, here. You see this image, right?
Yes, sir.
So let's pull it down here. So
Okay, sir.
I think this will take an entire eternity to reach there. We'll have to do something else. Yeah, perfect. Okay.
Yes, sir.
So I feel that this is a really good problem for understanding what's happening everywhere and how to identify limiting reactants and fractional components or whatever. So let's start this. A bit of physical understanding of what's happening in a problem is always beneficial for understanding what types of products are you generating and what are the different states of the product. For example, you can really check right over here that that gaseous reactants are reacting together and producing a gaseous form of water, that is H2O, that is effectively water vapor, and a solid form of sulfur. And of course, since this is solid, it will precipitate down somewhere. Okay.
Yes, sir.
or maybe not down, it might just get stuck on the walls of your reactor chamber or something.
Yes, sir.
Okay, so that is also important to understand how the reaction is happening. Anyway, so when you are obtaining natural gas, that is, something like a lot of methane in that and a lot of other components as well. So there are different types of natural gases. For example, in one site, you drill a hole and you are getting pure natural gas. And on another side, you are drilling a hole, but you are getting a sour natural gas, not a pure natural gas. So sour natural
Okay.
gas actually contains hydrogen sulfide, mercaptans. You might have heard about ethyl mercaptan
Yes.
that gives that typical pungent smell in your LPG gas cylinders. The one that we are using in our homes for cooking. Okay,
Yes, sir.
so
Yes,
the
sir.
smell that is given is actually a mercaptan compound and other sulfur compounds. So all of these are represented by the hydrogen sulfide gas, that is H2S right here. Okay,
Yes.
so we need to remove this somehow so that we are getting pure CH4, because this is not useful as a fuel, but this actually, gives a pungent smell like rotten eggs or something, or like a rotten smell into the gases. So what we are doing, we are flushing the entire thing. This is the test process. So in this process, what we are doing is that, for example, we are supplying a gas stream of maybe natural gas, which also contains H2S additionally. And we are flushing everything with an SO2 excess uh, in a gas chamber. Okay.
Okay.
Now, what's happening as this reaction is proceeding somewhere right here? Sulfur starts depositing at the bottom, given gravity is right here. Solid sulfur starts depositing here, and all this becomes water vapor, and we are collecting everything outside. Okay, and we are also scraping out the sulfur that is being deposited here.
Okay.
So this is what's happening physically. Okay,
Okay.
you should always, whenever you are solving some kind of reaction, you should always make these mental diagrams for a better understanding of this of the entire problem. For example, here you are not required to calculate the energies, but if you are also required to calculate the heats of formations or the enthalpies, for example, the total energy would be given as half rho v squared plus this type of thing plus gz1, something like this. You might have uh, seen this expression somewhere else, right? Have you?
Yes, sir. Bernoulli equations, sir.
Yes, a similar thing. So if you were to have to make an energy balance in this part, then you need to know where things are entering and how things are exiting.
Yes, sir.
So uh, visualizing the entire process in your mind, in your head, and creating a figure out of it and an image out of it is always beneficial for any type of problem. So this problem actually can be extended to hundreds of types of problems. So that is why I always remember to create a mental map of what's happening inside the process. Okay.
Okay, sir.
Anyway, uh, going ahead, now what we are having is that the test stream that is entering this gas chamber, since that is cluttered now, I'll be doing another thing right here. So this part contains 20% of H2S and 80% of CH4. Okay, and it's already given by mole, right?
Yes, sir.
And it is combined with pure SO2 in the gaseous form, and this produces 5,000 kilograms of sulfur in the
Yes,
solid
sir.
form. And, you know, this is the product gas.
Yes.
Now the point is, in this reaction, there could be two things happening. One would be that you are supplying all these gases in their stoichiometric formulation, and the entire thing is getting converted into water vapor and sulfur. So that implies that in the product gas, you'll not be having any type of hydrogen sulfide or methane or SO2 or anything, right? You'll only have water vapor and sulfur.
Yes.
However, if I do not supply these parts in their stoichiometric ratios, then obviously the excess gases, that whatever you have, maybe it could be this or maybe it could be this, they will just get flushed out along with the product gas.
Yes, sir.
So how do you identify if that is happening or not? Because you have this product composition, In the product gas, you see that there's a ratio of SO2 and H2S is 3. That implies that the product gas also contains both of these reactants. And this implies that the reaction is incomplete. It is not complete, okay?
Okay.
So this is how you, now, as soon as you understand that the reaction is still incomplete, then that implies that there must be a limiting reactant, there must be an excess reactant, and whatever extent of reaction, and all those things come after this. So the first step is to ascertain if the reaction is complete, okay?
Okay, sir.
Now, if the reaction not complete, only then you start doing all this limiting reactant and excess reactant and yield and all that stuff, okay?
Yes, sir.
So remember this point. Anyway, now the language of chemistry is mole. Do you actually know why do we talk in moles?
In most are considering that equation, sir. By
Yes,
that equation.
so that is right to a certain extent, because moles represent particles. Particles means they could be molecules, or they could be atoms, or anything, right?
Yes, sir.
So 1 mole of anything contains the Avogadro number and A of particles.
Yes,
So
sir. Yes.
since this is not a fission reaction, remember, a fission and fusion reaction, anything of that type would convert the entire species into something else. So since this is not that type of reaction, it is not breaking the bonds between all these things, mole concept can be applied. Okay?
Okay.
So
Okay.
if you've got a nuclear reaction, then you need to be really careful before you try to apply all these things, okay?
Okay, sir.
So, all right. So here we have that you've got, again, since the reaction is already balanced, let's take the unbalanced form of the equation and balance it ourselves. Why not? Okay.
Okay,
Now, I'll tell you the short trick, really short trick for balancing equations. Okay.
okay, sir.
Excuse me. So the first thing that you need to do, you might as well note these points down, or anyway, I'll be uploading these videos to YouTube very soon. Find the least occurring element. Okay.
Okay, sir.
Now you see that on the left hand side,
Yes, sir.
you've got 2 sulfur, 2
Yes, sir.
oxygen, 2 hydrogen.
Yes, sir.
On the right hand side, you've got 2 hydrogen, 1 oxygen,
One
and
sulfur.
here you've got 1 sulfur. Okay.
Yes,
Now,
sir.
don't touch this one. Reason being, the second part is find the free species.
Okay.
There will be oftentimes, you'll be having individualized species like H2, O2, N2. Okay.
Okay, sir.
Now, why do I suggest to find the free species? Is that because you can actually add any type of coefficient here to balance the number of atoms of hydrogen, right? So this will become 2x. So x could be, it could be 2.5, it could be 2, it could be 1. So
Okay, sir.
this is actually a free control, whatever number of atoms you are falling short of or you are getting excess, you can just balance it right away x.
Okay, sir.
So the first thing that you need to do is to balance the conjugated elements. For example, the conjugated elements are H, right?
Yes.
Here it is connected with O, here it's connected with S. So focus on that first. Once there is an unbalance, the sulfur you can balance anytime. That's my point, right?
Yes.
That sounds reasonable, right?
Yes, sir.
So the first thing that you do is balance the hydrogen atom. So you see that the hydrogen is already balanced, right?
Yes.
So we don't need to care about that at the moment. Next, so I told you that don't care about the sulfur atoms at the moment, right?
Yes, sir.
So now we check out the oxygen atoms. Okay, here are two oxygen atoms on the left-hand side. Here is a single oxygen atom on the right-hand side. Okay,
Yes, sir.
then just write a 2 here. All right. Now, as soon as you write a 2 here, although the oxygen atoms are balanced, the hydrogen atoms have become unbalanced.
Balance.
So again,
Yes.
I'm telling you to not touch the sulfur at the moment, right? Because you can balance it anytime.
Yes, sir. Yes.
So since there is an imbalance in the hydrogen atoms, what you do is write 2 here. So now it's 4 here and it's 4 here. The hydrogen is balanced. And you might now worry that the sulfur is now unbalanced because here there is only one sulfur and here there are two sulfurs, right?
Yes, sir.
So that is why I told you do not touch the free species. So now you have the freedom of writing, and wait, this is SO2. I'm sorry about that. Right, I'm sorry about that, really. So this is SO2, not O2. Okay.
So, yes.
So
Three
yes,
sulfurous
so
three.
yes. So the other things are unchanged, right? Only the sulfur is now unbalanced. So here, so this illustrates the importance of leaving out the free species even better. So you have two sulfur molecules here and one sulfur atom here, sorry, not molecules. So there are total 3 sulfurs here, okay?
Yes, sir.
But here you've got only one sulfur. So what do? Just write 3 here. That's all.
Yes. Yes, sir.
So that is the beauty of free species. When you've got a free species, you can balance it as however you want. Okay.
Yes, sir.
All right. So here's the final equation: 2H2S plus SO2 gives 3S plus 2H2O. Now just check it out real quick. 2 oxygen here, 2 oxygen here.
Yes, sir.
3
Correct.
sulfur here, and 2 plus 1, 3 sulfur here. 4 hydrogen here, 4 hydrogen here. So our equation is balanced, right?
Yes, sir.
And this is how it looks, probably looks upwards right here. It's identical, right?
Yes, sir. Same.
So in this, you see, right, that in this type of approach of solving the problem, you don't need to have any equations or anything like degree of freedom or anything. Is that right? Hello?
Yes, sir. Yes, sir.
Yeah. So just remember these 2 rules, and the rest is history. Anyway, so
Okay.
now you can understand. We'll also take one very complicated equation that you can solve using this identical rule. So we'll also do that. Don't worry. So here you have 2 moles of H2S reacting with a single mole of SO2 to give 3 moles of S sulfur and 2 moles of water vapor. This is
Yes, sir.
gaseous, this is solid, this is gaseous, this is gaseous, okay? Now, this is what the reaction wants, okay? The reaction wants to proceed like this.
Yes, sir.
But it is obviously not necessary for us to listen to the reaction, right? We don't want this, maybe. The reaction
Okay.
wants this, but we don't want this. So we are supplying arbitrary quantities of, let's say, hydrogen sulfide and SO2, and we leave it to the reaction
Okay.
to adjust its own values, okay?
Okay, sir.
So we don't care about the stoichiometric ratios at the moment.
Okay, sir.
So the reaction will manage itself, and that is why we are getting these weird values. Like we are getting the reactants in the product, and we are getting the entire product gas is mixed up. Okay, so
Yes.
what we know, in any problem of mole concept, you need to approach it in the reverse. Okay, so
Okay.
you actually know. Let's start from here. You have time, no? 10 minutes more, maybe?
Okay, sir. Okay, sir. No problem.
Let's start from here, okay? Reverse it. So we have 5,000 kilograms of sulfur, okay?
Yes, sir.
That is written here, 5,000 kilograms of sulfur. Now, why there is a logic behind this? Why am I telling you to approach this reaction in the reverse order, suppose you have a product, okay, sulfur. So you know that this entire product is being formed due to the reaction between hydrogen sulfide and sulfur dioxide, right?
Yes, sir.
So that implies that there must be some reaction metrics, that is some stoichiometric ratio that has combined together to yield 5,000 kilograms of sulfur. Now, there could be another scenario where you were already supplying some sulfur in the reactants, right?
Yes, sir.
So what would that imply? That this 5,000, let's say I'm supplying 100 kilograms of sulfur earlier in the reactant side, okay?
Okay.
So that would imply that the 5,000 kilograms out of this, 100 kilograms have been supplied by us, and the rest of the 4,900 kilograms have been produced by the reaction, right?
Okay.
So this is something that you need to keep in mind, okay? At this point, since all of this is being supplied by the reaction, this is something that will get us the closest to the reaction, okay?
Yes, sir.
Because this is completely natural, a natural consequence of the reaction. If the reaction had not happened, this would not have formed.
Okay, sir.
So that is why we first target this part. Now, as I told you that the moles are the language of chemistry. So 5,000 kilograms of sulfur is 5,000 over 32 kilomoles of sulfur, right?
Yes, sir.
Now, 5,000 over 32 kilomoles of sulfur, if you are getting right here, then that would imply that according to the reaction, what has reacted? 2H2S plus SO2 gives 3S. Now forget about the kilograms, right? They will convert everything into moles, okay?
Yes, sir.
So this is 5,000 over 32 kilomoles over right here. So that implies that 1/3 of this would be the amount of SO2 formed.
Yes, sir.
That would be 96 kilomoles, okay?
Yes, sir.
And 2/3 of this would be the amount of H2S formed. That would be 10,000 divided by 96 kilomoles. Not formed, reacted, sorry, because it's on the reactant side. And an identical amount would be the amount of water vapor that is formed. Okay?
Yes, sir.
Now, the problem is, these are the reactions requirements. The reaction
Yes.
desires the reaction to proceed this way, okay?
Yes, sir.
But our desires are not equal to the reaction's desires, okay?
Yes.
So we are supplying an arbitrary amount of H2S, we are supplying an arbitrary amount of SO2. So we'll obviously get, we'll obviously have a lot of excess of this H2S or SO2 or whatever. But this is how the reaction will proceed, no matter how much amount of gases you supply, right?
Yes, sir.
So now what we are having here is that since this entire sulfur is being produced due to the reaction of these two species, we can find out the amount of species that have reacted to be these values, right?
Yes, sir.
However, in this part, in this gas chamber, you are given that the amount of SO2 to H2S in the product gas is 3. That implies that a certain volume of, let's call it amount, not volume, maybe it might be confusing, SO2, H2S still remain in product, right?
Yes, sir.
And the ratio of H2O and H2S is 10. And H2O and H2S also remain.
Yes.
Okay?
Yes, sir.
Now the trick is, the trick right here is to identify what is formed only by the reaction. Okay?
Okay, sir.
So you need to find all the components, all the species that are formed according to the reactions desires, okay?
Yes, sir.
So both of these were not supplied by us. These were all formed due to the reaction, right?
Yes, sir.
So only the reaction is truthful. Whatever values the reaction will give, these are the absolute truths.
Yes, sir.
So you need to focus on them. So since the reaction is yielding a total of 5,000 over 32 kilomoles of sulfur, then this necessarily means that you'll be having 10,000 over 96 kilomoles of water vapor in your reaction, you know?
Yes, sir.
Because there's another catch here, right here. This is because you are not supplying any water vapor in the reactant side. No H2O, right? If you had you supplied some water vapor, or your gas chamber might have been moist, so on the reactant side, then there would be an excess of water vapor. Maybe the total number of kilomoles would be 11,000 over 96. Then you cannot say all of this is coming from the reaction, right?
Yes, sir.
So you need to correctly identify at the moment. This is the key that will help you to identify the limiting reactant, okay? So make sure you internalize this very well.
Okay.
So you need to identify what exactly is being formed due to the reaction. So you know that the sulfur is being formed exactly due to the reaction. You know that the water vapor is also being formed exactly due to the reaction, and you know this amount, right?
Yes, sir.
So this implies that since you are given the amount of H2O to the amount of H2S is 10, this implies that 10,000 over 96 divided by, let's say, XH2S. And let's denote the remaining part as R, okay? This is 10. And this was implied that the remaining part of H2S is 1,000 over 96, right?
Yes, sir.
So this remaining part, you need to understand why is this part remaining. So this means that this must have been supplied in excess. So that's why this is remaining, right?
Yes, sir. Yes.
So this was not required by the reaction, but so it could not react it because the reaction will only proceed according to this part. Okay.
Okay.
So this implies the total number of H2S moles would be X star H2S plus XR H2S. And let's say this X star is the amount that has reacted, right?
Yes, sir.
Right?
Yes, sir.
So the amount that has reacted is already governed by the reaction mechanism, right? And
Yes, sir.
you know exactly that the amount that has reacted is 5,000/96 kilomoles plus the remaining part that is 1,000/96. This entire thing becomes 6,000/96 kilomoles.
Yes, sir.
And this becomes 1,000/16 kilomoles.
Yes,
So
sir.
now you know that out of the total hydrogen sulfide that you had, some part of that has reacted and some part of that is still remaining in the product.
Yes.
And you have perfectly resolved everything, okay?
Yes.
The next information that you are given right here is this. The ratio of the SO2 to the H2S in the product gas is 3.
Okay.
So the product gas, you know, what does the product gas contain? Let's revise it. This contains the sulfur. Can you tell me the other components, please?
Sulfur, water, again with these remaining hydrogen sulfide and SO2.
Yes, so this contains XR, H2S, and XR. R means remaining, right?
Yes, sir.
SO2. Okay, this is the composition of the product gas. Now, you already have this, you already have this, you already have this.
Yes, sir.
There is one variable that is left. You don't know this.
Yes.
But you've got another data point that helps you obtain this.
Yes, sir. Ratio of SO2 to H2S.
Right. So you can simply write it as like this. XR SO2 divided by XR H2S would be equal to 3, right?
Yes, sir.
Now you already know XR H2S.
Yes, sir.
So just get it something like this. You'll be getting 3,000/96, right? Kilomoles.
16.
Sorry, did I do some error maybe?
Oh, no, sir. 96. No, 96. Only 16.
No, you need to multiply it by 3, right?
Yes, sir. 3000 by 16, sir.
No, here, you are talking about R, you know.
Yes, sir. Sorry, sir. Sorry. Okay, sir.
Yes, so we need to, yes. So you need to be really careful at this point, you know, that this is the total amount that we supplied, you know, in the inlet.
Yes, sir. Yes, sir.
This is
Sorry,
the
sir.
one that is remaining. That's all right. That's perfect. You know, making mistakes helps you learn. So this is 5,000/6, 500/16 kilomoles, right?
Yes, sir.
Now you also know X star SO2
Yes, sir.
given by the reaction plus XR SO2 would be equal to the total number of moles of H2SO2, right?
Yes.
This implies that extra SO2, what was that? Do you remember? It was 10,000/96 kilomoles. Plus, right? And there is another advice that I'd give you. Unless there are really weird numbers like 7 and 35 and 19, these values, always keep your values as fractions, right?
Yes, sir.
So later when you are, you know, calculating them and reporting them, you can have a precise value of the answer. Else, what you'd be doing, you would be accumulating there. For example, if you report some value as maybe let's say 10.37. And the actual value that was coming out was 3.6165, let's say 656, okay?
Yes.
And you report it like this, then there is a certain error that is being introduced here. And again, when you use this value for further calculations, then there might be, your value might be coming as 19.287, and you are again reporting it as 19.29, but the actual value was 19.33.
Yes, sir.
So this error keeps accumulating exponentially, e to the power x type of error. And in the end, if you are actually rounding off too much and finally calculating and reporting your answer, the difference could actually go, maybe you are reporting an answer of 7.5, but the actual answer is 8.9. So this is entirely wrong, you know.
Yes, sir. Yes.
So that's why it is best to always keep your answers as fractions so that they can be readily converted into decimals anytime you want. Okay?
Yes, sir.
So now what do you have? You have SO2, you have xt of H2S. Okay? You got everything actually.
Yes, sir.
So now you need to calculate the limiting reactant, fractional component, and the feed rates of H2S and SO2 streams. Okay? So now when we are talking about, you know, the limiting reactant. So as I told you, the limiting, you know, if you supply some, just a moment. Now, to avoid further, I think the limiting reactant calculations in the video that you watch has some equations like some sigma, blah, 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 something like this, right?
Yes, sir.
And some degree of freedom f0 minus f1, something like that, and divided by something. If it comes negative, then it becomes something. Then if it comes positive, then it becomes something else, right?
Yes.
Yes or no? Hello? Yes?
Yes, sir.
Okay. So you've got this reaction. This is 3s plus, what was that? H2O, right? And here a 2. Now you know the total amount that we are supplying right here, right? This is 30,000 over 96 kilomoles. And the H2S is 6,000 over 96 kilomoles. Okay?
Okay, sir.
Now, you need to like really be careful at this point. You know, the reaction for identifying limiting reactant, okay?
Yes.
You need to understand the reaction's desires. What the reaction wants, you need to understand that and relate to that, okay?
Okay, sir.
So what the reaction wants is
2 moles of H2S,
yes.
1 mole of CO2.
So for every 2 moles of H2S that is reacting in the reaction chamber, the reaction wants only 1 mole of SO2, neither less, neither more.
Yes.
Okay? So just approach it both sides, both ways, okay?
Yes,
Let's
sir.
say you've got total 6,000 over 96 kilomoles of H2S. Then what does the reaction want? It wants only 3,000 over 96 kilomoles
Yes, sir.
of SO2.
Yes.
What are you actually giving to it? You are giving more than 4 times of this value, right?
Yes, sir.
So this implies that SO2 is being supplied in excess.
Yes.
And since SO2 is being supplied in excess, that means the limit to the reaction, I mean, the reaction will stop when all the H2S is reacted, right?
Yes.
You understand my point, right?
Yes, sir. Yes.
The reaction must stop because, for example, if 5,000 over 96 kilomoles of H2S have reacted, you still have 1,000/96 kilomoles left. And at this point, only 2,500/96 kilomoles of SO2 have reacted, right?
Yes, sir.
So as soon as these 1,000/96 kilomoles of hydrogen sulfide have reacted,
Yes, sir.
this would imply an additional 500/96 kilomoles of sulfur dioxide, right?
Yes, sir.
But still, you've got plenty. You can react 3,000 or you can react 4,000, 5,000, 10,000, anything, but you've still got an excess, right? So what is limiting the reaction? I mean, you understand the limiting reactant as something that stops the reaction, okay?
Yes, sir.
Just understand it as a numerical tolerance. When do you need to stop the reaction? When does the reaction stop by itself? What is its desire? What does the reaction want? The reaction wants to react only 6,000/96 kilomoles with 3,000/96 kilomoles of sulfur dioxide, but you're supplying much more than that. So of course the reaction will not touch this part, the leftovers.
Okay.
Okay, so and the entire hydrogen sulfide gas will be the limiting reactant of this reaction. Okay,
Okay.
so did you get a clarity out of whatever was done?
Yes, sir. Without using those formulas, we can do.
Yes, without
Yes.
using all those formulae, you don't need those formulae at all. So we could have actually discussed another problem, but maybe we'll keep it for the next time.
Okay.
So next time, if you want, you could join maybe at 5:45 or
Okay.
6, whatever. I mean,
Join. In that, my laptop is the problem, sir. Something I
yeah,
don't
yeah, yeah.
playing.
No problem, no problem. You can take a look actually. Maybe you can have it repaired or something.
Yes, sir. Yes,
Or
sir.
else you could continue, you could just continue using your cell phone, maybe. Anything, but just join at 6. So we could actually go in the direction you want. Because today, since there was no one, I was just randomly picking up stuff to do. Because I have to do something, right?
Yeah, I choose only. I think I am the only choosing this subject online
So
questions.
sorry. I did not get it.
Is there any other participants, sir?
No, 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 no. I was also surprised that there is only one person, that is you. And if you were not here, then I would be teaching myself.
Sorry, sir. Actually, I tried last week also, sir. But
Yes, actually you were there, but I don't know what was happening. So I thought that it was some random person who had joined, so I did not care about it.
yes, sir. You asked me about the robot or something, but I am replying, but it is not audible to you, sir.
Right, right. So I was thinking that someone, deliberately entered this chat, entered the meeting to create chaos. So anyway, that is fine. Now I understand that you are a legitimate person, so I won't be asking if you are a robot. Anyway, so did you get a clarity of the limiting reactant part and excess reactant parts or those things?
Yes, sir.
Without, can you speak into the microphone, please? I'm not hearing you.
Yes, sir.
Yes, yes. So without any equations and all that stuff. So there are, even more complicated equations like, where's the pen? Yes. So there is one thing that I really liked this part in the reactions that were discussed in the videos.
Yes.
This one. So the formation of allyl chloride,
Yes, sir.
and the other reaction is this C3H6 gaseous form, C3H6 CO2. This is not required, okay? So
Okay.
what's happening here is that the chamber is actually being supplied with one side of CO2 gas, another side with propene, and the products are three, One is allyl chloride, another is residue, this one 2-chlorine, and another is HCl, right? So now, as I said, you need to understand what the reaction desires, right?
Yes, sir.
The needs of the reaction, you need to understand that. So you are supplying an arbitrary amount of chlorine, let's say some 100 moles, okay?
Yes.
Now you cannot expect that 100 moles of chlorine will be entirely utilized in this reaction.
Yes.
There will be a certain amount of, now students typically do, they see there is the stoichiometric coefficient here is 1, the stoichiometric coefficient here is 2, and there are 2 reactions. So some people, what they do, they just supply 50 moles here and 50 moles here.
Yes, sir.
So that is not the case, because the kinetics of these 2 reactions are entirely different. The rate constants, you know,
Yes.
you must have already heard about it. HCl times allyl chloride divided by C3H6, let's say call it propene, and divided by Cl2. So this is entirely different compared to that. So the amount consumed per unit time will be obviously different, right?
Yes, sir.
So you cannot directly say how much amount is being consumed, and that is the problem that you need to calculate. Maybe X moles are being consumed here, then 100 minus X moles are being consumed here. And again, once you distribute these X moles right over in both the reactions, the X entirely might not be consumed. Maybe only maybe only Z is being consumed. Then the product gas would be having X minus Z from here of chlorine, right?
Okay.
And here maybe, 100 minus X and only W is being consumed. So the product gas would be having 100 minus X minus W of chlorine, right?
Okay, sir.
So in combination, from both of these 2 reactions, the total amount of chlorine that you'd be having is this, that is outside. So this is coming from both the reactions, reaction 1 and reaction 2, right?
Yes, sir. Yes.
So that takes a different approach that maybe I'll cover in the next class. So I'd request you to, if you have any types of doubts or questions in these lectures or anything, feel free to collect them all in one place, and then we can discuss in the next live session, right?
Yes, sir. Sure, sir.
And any doubts you might be having in these types of balancing reactions and stoichiometric reactions, you can all bring it. I'll welcome everything, right?
Okay, sir.
And I don't think you have a lot of problems in the numerical part, right? Numerical methods.
Yes, sir.
But the next time we'd be discussing the system of nonlinear algebraic equations. Okay.
Okay.
So you could, if you want, you could just go through all of these videos and then collect your doubts in one place, and also some questions and anything. So that would make the session really meaningful for you. Else,
Yeah.
yes, so I'd be doing something random, and that might not be required by you. So there will be a mismatch in the wavelengths. All right. So did you like today's session? Maybe,
Yes, sir. I like it.
hopefully. I mean, maybe, hopefully it was not boring for you. You
No,
learned
sir.
a few things.
Yes, sir.
So the key takeaways would be to find limiting reactants without formulae,
Yes,
and
sir. Yes.
find the excess reactant without formulae, and how to balance using intuitive techniques instead of, mathematical formulae, because, there are hundreds and thousands of mathematical formulae that can be developed, but
Yeah.
you might not remember all of them. So
Yes, sir.
you need to understand the ethos, the fundamentals of certain concepts. So once you do that, you can always recreate your mathematical formula in a way that that is suitable to your needs, right? and the initial guess. I guess this will help you in your doctorate. So
Yes.
how to, think about the initial guess. So we can talk about it. You might be solving a lot of laminar flow problems, Navier-Stokes equations, right?
Yes.
Numerically using some ANSYS fluent or something, right? Maybe or maybe not. I'm not sure. If you are doing, are you working in CFD a bit? Maybe.
No, sir.
Okay. So anyway, even if you are not working, you might be needing some initial guesses. So understanding the physical nature of the problem and what's happening always gives you a good guess. And a good guess will always give you a good solution. So that was the key takeaway from that. Okay. So what is your name actually? Maybe you could tell me. I cannot hear you. Maybe you can write it down.
Chanakya, sir.
Oh, Chanakya. Nice. Good name. Good name. Anyway, so I'll be stopping the sharing of the screen and I'll be stopping the recording. So we'll